All right, everyone. Welcome to lesson 12. We're going to go over volumes of revolution part 2. So last time, as I said, we were talking about finding volume using integrals. And the way we did that was we remembered what a Riemann sum was, and we went back and effectively made a Riemann sum out of each shape that we wanted. We broke it up into a bunch of different chunks, and then we added together all of those tiny little chunks to get the total amount of volume for a shape. So that was the volume part. And now what we're going to do is we're going to apply this knowledge to finding volumes of revolution. And what a volume of revolution is where we take a two-dimensional area and we spin it around some kind of axis. And in doing so, we end up creating some kind of three-dimensional shape. And the volume of that shape we could figure out using techniques we're going to do today. All right, so let's go ahead and look at an example here. Example 1. Find the volume of the shape obtained by rotating the area between the curves y equals x and y equals root x around the x-axis. Okay, so that's our question here. That's the question we're going to try to solve. All right, so as with any of these volume problems or any of the applied stuff that we're going to be doing starting on Friday, we want to draw a picture to help us out. So I'm going to draw a picture, and I'm going to draw a picture of these two curves. So square root of x starts here, and it goes up like this. And then x is the line that goes perfectly diagonally through the origin. And these curves end up meeting up here. All right, and what we're doing is we're taking this area right here, and we're spinning it around the x-axis. So what is the shape going to be? It's almost going to be kind of like a bowl. Like the outside is going to be curved to be like a bowl, but then the inside is going to be completely flat and diagonal. And it's almost going to be kind of like a sort of like an inverted cone in the middle here once we spin this around. And what we wanted to know, maybe we're making the shape for some kind of application or something, we need to know how big it is to order enough material for making this item. So how are we supposed to figure out the volume of this shape? So first of all, what we're going to do is I'm going to figure out the volume created by only spinning this curve around, and then I'm going to subtract away the volume made by spinning this curve around. What do I mean by that? Let's say I only draw square root of x, right? And let's just stop it right here because this is where it stops in the picture above. All right, so we're going to spin this around. Now, how are we supposed to figure out what the volume of this is? This is like the filled in version of the shape up here. Well, what we're going to do is we're going to apply the same philosophy that we had last time. We're going to break this up into chunks, figure out how much volume each chunk takes up, and then add all of them together. So if we, let's say we have a very thin rectangle right here. Let's say this is our rectangle. And we're spinning this around. So if we spin around this rectangle, the outside edge is going to end up making a circle, right? So we're effectively going to end up with a disk when we spin this around. So we spin it around here, and then we spin it around the other way as well. So we're making this very thin disk right here. All right. So then what is the volume of this disk? Well, technically, this is a very thin cylinder, right? So this is a very thin cylinder, and the volume of a cylinder is going to be its height. And our height, what am I going to call the height variable here of this cylinder? Oops, I just wrote it. I just wrote it subliminally. Yeah, so this is the x direction. So if we have a tiny amount of distance this way, it's going to be called dx. So dx is like the height of our cylinder, but it's very, very thin. And then we multiply that by the area of the circle, So that will be pi r squared. Okay, now let's see here. So let's see what the radius is. So if I start here and go out to the outer edge of my circle, this length right here is going to be my radius, right? So what's another name for the distance from the axis up to the curve? We talked about this last time. It's y, right? Whenever we want to measure a vertical distance from the axis to the curve, it's going to be y. So we have pi y squared dx. And then I think this problem looks familiar. We have y's here and x's here, but we need to make sure things are in x's when we do our integral. But the good news is that we actually already have a relationship between y and x. We know that y is equal to root x here. So we end up with pi x dx. So this is going to be the volume of one of these. And then if we were to throw this into an integral, we would get the volume of this entire shape right here. Now what we're going to do is we're going to also do this for the smaller shape here. So here we have y equals x. Say it goes this far maybe. And we're spinning this around, and this will make an inverted cone right here, or like a tornado shape. All right, and then if we do the same thing here, we're going to have the same formula for our shape because they're both cylinders, or these kind of filled in discs here. The volume of this disc is going to be pi r squared dx, or pi y squared dx. But this time our y is different. We're using y equals x for this. So we're going to have pi x squared dx for this right here. Now, if I want to get the shape, the volume of this shape here, what I can do is I could take the volume of this shape and then do what? I want to get this volume, and I know what this one is and this one is. What can I do? We can subtract them. That's right. So the volume for this, we're going to combine these together. The volume for a disk here will be pi x dx minus pi x squared dx, because we're effectively taking this chunk that we're getting and subtracting away this chunk that we're getting to get this one. All right, so then if we combine this together, we have pi and then x minus x squared dx. And then when we add all of these together, we'll get our volume. We're going to have the integral of pi and then x minus x squared dx. Okay, now we come up with the perennial question here. What are the bounds of our integral going to be? So the bounds are going to be x values. The bounds are always whatever variable this is. It seems like the lowest x value where these guys are going to have area is x equals 0 here, right? Okay, and then this kind of arches up. It's a little bit bigger, but then it crashes back into the curve up here. Does anyone know what this x value is going to be up here? It's going to be 1, right? And how would I know that? You know, maybe these curves were more complicated. It was a bit harder to see. How would I know that? One thing we could do is we could set them equal to each other. So we could have x is the square root of x, which is the same thing as saying when x squared equals x. That happens at 0 and 1 right here. So if you ever want to know, like if you have these two curves kind of intersecting like this, set them equal to each other and see what x values you get. All right, and then now we just need to do this integral. And thankfully, just like all the other ones we've been doing so far, this integral is actually pretty straightforward. So we integrate here, use the power rule. We use the power rule here as well. We go from 0 to 1. Then I plug 1 in here. Okay, 1/2 minus a third. And I plug 0 in. But if I plug 0 into this polynomial, I'm going to get 0. So I have pi times 1/2 minus a third. 1/2 minus a third gives me 1/6. So the volume of this shape is going to be pi over 6. Now there's one property that the volumes for all of these shapes will have. What's one property that a measure for volume needs to have? It needs to be, well, it does need to be cubed. That's true. So this is pi, and then we would say like meters cubed or something if we wanted a unit. But also it needs to be positive. If we were to make this shape, we wouldn't say, oh, we have like -3 meters cubed of this shape. That doesn't really mean anything. So we need to make sure that our answer is always going to be positive for this. And another way to see this is going to be positive is we're looking at pi r squared. This is a square, and pi is positive and dx is positive. So everything's going to be positive here. All right. Does that mean that area can be negative? Yeah, so if you remember back from Calc 1, the integral technically tells you the signed area. So if we have, like, say something like this, and we integrated here, then we would get 0 because these were equal and opposite. But for this, we're always going to get something positive. Yeah. That's right. Yeah. So we have a question here. What if we accidentally subtracted this the wrong way? So we did maybe the x squared minus the x. What would happen then? We would end up getting the negative of what we want here. And then we could use this fact to check our work and be like, wait a minute, we shouldn't get anything negative here. Now it's kind of weird, right? We would imagine that the x squared would be bigger than the x, right? Like in the long run, squaring a number is bigger than just the number itself. But for smaller numbers in between 0 and 1, it's the opposite. Like, for example, 1/2, if you square that, it gets smaller to 1/4. So it's going to be smaller than it was before. So for between 0 and 1, the hierarchy of functions for this is flipped around. All right. So anyways, now this isn't just true of this problem. So we could go through this process for every single problem like this for volumes of revolution, but that'd be kind of a waste. It turns out that there's going to be a formula that will work for all of them. And so the volume of revolution for a function of x going around the x-axis is going to be the integral from a to b. And remember, we get this a and b usually from setting the two curves equal to each other, or maybe setting them equal to 0 if they touch the axis. We're going to have the bigger one squared minus the smaller one squared dx. And one way to imagine this is we can imagine f of x is our outer function, and this is our inner function. Or this is further from the axis or closer to the axis here. So this is going to be the general formula, and this is going to be called the Washer method. Now, why does this have the name the Washer method? Well, if I took this shape, this bigger disk that I heard earlier, so I took this bigger disk, and then I subtracted away the smaller disk, then we end up getting the shape of a washer, which you use in construction and stuff like that. So this is going to be the Washer method. Now this works for f of x spinning around the x-axis specifically. We're going to learn another technique for spinning things around the y-axis shortly. All right. So both of these are squared. That's right. Yeah. So kind of like how we had root x earlier, and that ended up being squared to be x. We also square the smaller one, x, into x squared. Can I explain the bounds one more time? Yeah, so we just put the lowest x value where we have the area and the highest x value. And almost always that ends up, you end up getting those values by setting the two curves equal to each other, your lower one and your higher one. That's how you get those bounds. And remember, the general philosophy for any bounded integral, you always want your bounds to be wherever the object is. That's the key philosophy behind picking your bounds. All right, so why don't you guys give this a try here? So why don't you guys try to use the Washer method to find the volume of the following? Let's see here. So practice 1, use the Washer method to find the volume obtained by spinning the area between y equals e to the x, y equals 1, and x equals 2 around the x-axis. And my hint for this, draw a picture. Draw a picture of what this looks like. Drawing a picture helps for all of these problems, both for the volume ones that we're doing now, and then also for the applied problems, which we're going to be doing next class. I'll give you guys a few minutes to work on this. So it's the shape made by the three lines at their intersections? That's right. So if you draw all three of these, there'll be one patch of area that's between all. All right, guys, give me another minute or so, and then we'll go over this one. And you can keep working on it while I'm explaining the beginning. I know this might not be enough time to finish it. I just need to make sure we need to get far enough in the lesson here. Why we use the Washer formula for 3 lines? So remember, only 2 of them are functions, e to the x and 1. The x equals 2 will just be your upper bound for the integral. It kind of just cuts off there. So if you square e to the x, remember your exponent rules, you just multiply the 2 by the x. So it's going to be e to the 2x. All right, guys, I'm going to get started on this one. So as always, we should draw a picture to see what's going on with this. So I'm going to draw the curve y equals 1, which is just a flat constant line here. I'm going to draw e to the x. Now I know that at x equals 0, e to the x will also be 1. So this is going to be one of our points of intersection. And then we go up exponentially like that. And then finally, we have x equals 2, which is a vertical line here at 2. So the area enclosed with all 3 of these is going to be this right here. All right, so let's go ahead and use our formula. So the volume is pi times the integral of the outer function squared minus the inner function squared. And remember, we're spinning around the x-axis. So the thing that's further away from the x-axis here is this e to the x. So we're going to have e to the x squared, which is going to be e to the 2x. Then our lower function, our inner function, is just 1, and 1 squared will be 1. And then finally, we need to figure out what our bounds are going to be. Now, it's pretty clear from drawing the picture that our upper bound will be x equals 2. This is the x value in which we stop having the shape. So we know we could just put a 2 up there. And then in case you didn't know where this point is, we could set e to the x equal to 1, and then we could take natural log of both sides. And we see that x is going to be 0 here. So we're going to go from 0 to 2 for this integral right here. Will the area being rotated always only be in 1 quadrant? Not necessarily. I mean, if this shape would have continued over here, we would have done it the same way. The only difference would be we would just have a negative bound. So it doesn't always need to be in 1 quadrant. All right, so let's do this integral here. The way we do the integral of e to the 2x is we just divide by that coefficient in there. So we get e to the 2x over 2. The integral of 1 will be x. And then we do this from 0 to 2. All right, so I'm going to plug 2 into here, have e to the 4th over 2 minus 2. Oh, thank you. I'm trying so hard to keep the formula. There we go. All right, so we have e to the 4th over 2 minus 2, and then we plug in 0. And it's really tempting to just be like, oh, well, if I put 0 in there, it's going to be 0. But remember, we're subtracting away e to the 0 over 2, which is going to be -1/2. And then when we put 0 in here, we're going to get 0. So if we simplify this, we get e to the 4th over 2 minus 5/2. All right. There we go. I used u sub to find the integral of e to the 2x. Is there a faster way? Yeah, anytime you have the integral of e to a number times x, all you need to do is just divide by that number. That's all you need to do for that. All right, there we go. So there was our practice here. Now we've answered 2 questions where we've spun around the x-axis, right? So it's only natural to ask, can we spin something around the y-axis? And the answer is yes, we can. There's no issue with that at all. So let's take a look at another example. Okay, find the volume of the shape obtained by rotating the area between y equals x, y equals root x around the y-axis. So we actually already know what this looks like. These are literally the same 2 curves that we had for the first problem here. So let's take a look at this. Yeah, so why can't we just turn our page around and do it that way? I'm going to explain that in a minute, because I actually had the same thought when I was learning this stuff, like, oh, just flip the page over and then, there we go. It's going to be the same thing. But take a look at this. It's going to be a little bit different. Okay, so here's our area. Now this time we're spinning around the y-axis, right? Now, if we think of carefully about what this shape is, the previous shape had a curved outside and a kind of a flat inside. This is going to be the opposite right here. This is going to have a flat outside, so the outline is going to be kind of like a cone, but then the inside is going to be kind of curving and then coming to a cusp down here. So this is actually going to be in a different shape if we spin this around the y-axis as opposed to the x-axis. So since it's a different shape, it may in fact have a different volume. All right, so let's go ahead and figure out the volume of this. And as always, we're going to try to break things into different chunks here. All right. Imagine, like, if you're having trouble imagining this, imagine that you're going to have like a cone, like a solid cone, but then there's this almost like golf tee shaped thing that's cut out of the middle of it. That's the shape that this is going to be. All right. Let me draw another picture right in shaded in the area. I think it'll be easier to see this. All right, so I'm going to take a rectangle right here, and I'm going to spin it around this way. So when I spin it around the y-axis, what I'm doing is I'm making what's called a shell. It's almost like a cylinder that's been hollowed out. You end up getting this shape right here. So imagine it's almost like a tin can. It's like a cylinder, but then it has all of its inside removed. Now we want to figure out how big this shell is. So how do we figure out how big it is? Well, what we could do is we could take the area of this rectangle right here, and then we're effectively taking this rectangle and dragging it along the path of a circle. So let's write this out. The volume of one chunk or slice or whatever you want to call it of this will be the area of the rectangle times the path it takes to get around the circle, which is the circumference of the circle right here. All right. So let's see here. So how are we going to write down the area of the rectangle? Well, the width here, we know what we're going to call that. What are we going to call this tiny little width? dx, right? Okay, so that's the width here. Now let me ask you guys this. What's the height of this rectangle? So if we just had y, we would have the question, which y do we go up to? So if we went all the way up to the bigger y, that'd be too big, but then the smaller y would be too small. So I see dy And I know what you guys are saying, you're talking about the difference in the y's, and that's absolutely right. So if I call this one y1 and maybe this one y2, this is going to be y1 minus y2, i.e. it's the functions that are subtracted from one another. And for this problem, we do root x minus x right here, because root x is the bigger function. All right, so that's going to be the area of our rectangle. Now let's see what the circumference of our circle is. So what's the formula for the circumference of a circle? You guys remember that? Yeah, it's going to be 2 pi r, right? Now we don't have an r on this problem. We just only have x's and y's. So we need to convert this to be an x and a y. Now let's see what a good name for our radius be. So our radius of this cylinder is going to start from this axis and go all the way horizontally to our rectangle. So we're measuring the horizontal distance from an axis to our curve. What do you guys think that's going to be? It's going to be x. You guys predicted correctly. So instead of writing an r, we're going to write an x instead. Just like how we can write any vertical distance from the axis as y, we could express any horizontal distance from the axis to our curve as x. So we're going to have 2 pi x here. So then what does that mean for our formula? If we kind of collect everything together, we have 2 pi x and then root x minus x dx. So this is going to be the volume of our chunk right here. Now, if we integrate, we're going to get the entire volume. So we're going to have 2 pi times the integral of x root x minus x dx. Okay, and then the bounds of our integral, one thing that is the same between the shell and washer method is if you use the shell and washer method on the same area, the bounds will be the same because we're doing an integral with respect to x, right? And our area begins here at x equals 0, and it ends here at x equals 1. So our bounds we found out in exactly the same way as before. So the bounds are identical between these two methods, but the actual formula is a bit different. All right, let's go ahead and do this integral right here. So if I multiply x by root x, I get x to the 3 halves. And then I do minus x squared. All right, let's see here. So I have 2 pi, and then I raise this power by 1 to be x to the 5 halves, and I divide by 5 halves. But of course, dividing by 5 halves is the same as multiplying by 2/5. All right, then here we have x cubed over 3. All right. So then all we need to do is plug in our 1 and our 0, and we'll be good to go. So let's see. We have 2 pi. If I put 1 in here, 1 to the 5 halves is just 1. So we have 2/5. And then I plug a 1 in here, and I have 1/3. And then, of course, when I put 0 in for these powers, those will all be 0. All right, now let's see here. Let's combine these fractions. This is 6 over 15 minus 5 over 15. So this ends up being 2 pi over 15. This is going to be our volume for this shape. And one interesting fact about 2 pi over 15 is 2 pi over 15 is not equal to pi over 6. This goes to illustrate that we can actually get a different volume by spinning it in a different direction. And it ends up making a different shape. All right. Are the bounds for this one based on the y coordinates? No, they're based on the x coordinates still. They're always based on whatever variable this is right here. Yeah, what's up? If I did dy, then my rectangles would have to be like this. Yeah, so what you could do, so what the audience is saying is, could we have made this a dy integral instead? And the answer to that is yes. We could have made this an integral of y and done it that way, but that way's a bit harder because we would have had to convert these to be x as a function of y, and then we would have had to set it up with the horizontal rectangles like this. I'm going to talk about that a little bit later, because that's a good thought. All right. Is there a shell formula like there was for the washer? Absolutely. So this isn't, of course, specific to these two functions, or x and root x. We can have a formula in general. So the shell method And it's called a shell because we end up getting these shells when we rotate here. The shell method formula is v is 2 pi times the integral from a to b of x, and then we have f of x minus g of x. Now notice that this x is part of the formula. It's not just because we have root x and x here. This x will be part of it no matter which functions we have, because no matter what, the radius of the shell will just be x. So this x is a permanent part of this formula. And the shell method works best when we have functions of x that we are rotating around the y-axis. All right. So with that in mind, let's go ahead and take a look at an example here. So practice 2, find the volume of revolution between the curves. Let's see. Y is 1 over x cubed, x is 1, x is 2, y equals 0, and we're spinning this around the y-axis. So go ahead and give this a try. Is there any exception to the shell and washer method? Not really. As long as you can make a coherent area, then no, this method should work for anything. Although these formulas are specifically if you're spinning around the y and x axes. If you're spinning around a different axis, like maybe x equals 2, then the formulas are a bit different. Is f of x closer to the x or y axis? F of x has larger numbers and g of x has smaller values. Remember, this is still a volume, so we want to end up having something positive. How'd you find the bounds again? You set the curves equal to one another. So I set root x equal to x, but I already did that in the previous problem for this one. Now, if they give you x values, those are likely to be your bounds if you have functions of x. What do we mean by smaller and larger numbers? Well, so in this interval, root x takes on larger values than x does. So you just want the function that is more vertical or higher up. The bounds for this one, 1 to 2, absolutely. G of x be x equals 2. So that's not really a function of x. We want y equals something, or f of x equals something for this. So it wouldn't be 2. Would be y equals 0. That's absolutely right. Bianca, it's whichever one's larger for the shell method. F of x be the 1 over x cubed? That'd be a good idea. And if you're ever unsure about which one's larger, just plug some numbers in and see what you get. What's the integral of 1 over x squared? Yeah, negative 1 over x. There we go. All right, give you guys another minute or so. Seems like pi is the consensus here. All right, let's take a look at this. So first of all, what we want to do is we want to draw the curves. So let's see, x equals 1. Maybe we could say that's right here. And then x equals 2. Oops. Thank you. All right. We got those. And then y equals 0 right here. And then 1 over x cubed. So 1 over x cubed, or 1 over x to a power in general, is going to look something kind of like this. Because the bigger the number that we put in here, the bigger our denominator is going to be, so we're going to end up getting small. So this in here is the area that we're going to spin around here. And it's going to end up making something that almost looks like a volcano or something like that, turn to the side. All right, so we have functions of, oh, wait, no, sorry. We're not spinning around this axis, we're spinning around here. That will not be what I said. Yeah, so we're spinning this around the y-axis right here. All right, so let's go ahead and use our shell formula. So the volume is going to be 2 pi, and then we have our integral. Now, the furthest left we go in our area is x equals 1, and the furthest right we go with our area is x equals 2. So those are going to be the bounds. And this one, we didn't even need to set anything equal to something else. We saw that our left and right bounds were just 1 and 2 here. All right, we have our x, which is in there by default. And then it looks like the higher curve here is going to be 1 over x cubed. And then the smaller curve is just going to be 0. So this is going to be our integral right here. Now, the nice thing about this is this simplifies well. This is going to simplify to 1 over x squared. And then what I do is I do the power rule to integrate this. So I have negative 2 pi over x for this. Because I raised this power by 1, so from negative 2 to negative 1, and then I divided by negative 1, giving me this negative sign right here. All right, and then finally, I'm going to plug in my numbers. So I plug in 2. I have negative 2 pi over 2. And then I subtract and put in the 1. So I have 2 pi over 1 minus pi gives me pi. So a very simple answer for this one right here. And I saw some people in the chat getting negative pi. Most often, if you get the negative version of an answer, that means you just flip the order of these here. All right, let's do one more example, and then I want to summarize all of this stuff. So we got a question earlier about having functions of y, or doing integrals with respect to y, rather than doing integrals with respect to x. And sometimes that ends up being more convenient for drawing these volumes or figuring out what they are. So we're going to learn how to do that as well. So for my third example here, I want to find the volume of revolution around the y-axis for the area between x equals cosine of y, x equals sine of y, and y equals 0. All right, so as for any of these problems, what we're going to do is we're going to draw a picture. All right, well, we know where y equals 0 is. That's going to be down here. That's not an issue. Now, x equals cosine of y, that's going to look something kind of like this. And if you're unsure what this looks like, you could plug in a few different y values and see what the x values are. So for example, if I put in y equals 0, I end up getting x equals 1. If I put in, say, y is pi over 4, I get x is root 2 over 2, which is smaller. And if I put in y is pi over 2, I get cosine of 0. Then we have x is sine of y, which is going to look something like this. Now this one, it might be a little bit hard to tell where the area is, but we need to remember it's between these three curves specifically. So this one, and this one, that means we're looking at the area right here. All right, and then what we're doing is we're spinning this around the y-axis. So how am I going to do this one right here? This one I'm going to use the washer method. And you might be like, oh, well, Dr. Manley, you just said back here with the shell method, if we're going around the y-axis, we should use that. But if we have functions of y, the situation is reversed. We use washer for functions of y around the y-axis, and we use shell for functions of y around the x-axis. And I'll describe that in a little more detail in a second. But suffice it to say, we're going to use the washer method here. So we have pi times an integral. We're going to have dy here. Now, this time we need to remember, we need to be careful about what our bigger function is and what our smaller function is. In this case, we should think of it more as an outer function and an inner function. So which one is going to be our first one here? What are we going to put first for this? Cosine, right? And since it's the washer, it's going to be squared. All right, and then that means our inner function, which is closer to the axis we're spinning around, will be sine. And so we square that and we get sine squared. Remember, a better way of thinking about this, especially when we're working with y, is this is outer and this is inner. We see which one's closer to the axis we're spinning around and which one is further away right here. All right, now we need to go ahead and do this integral right here. Oh yeah, well, wait, actually, before we do that, we need to get our bounds. Now this time, since we're doing an integral with respect to y, we pick the lowest y value that our area touches and the highest y value that our area touches. So what's the lowest y value that we hit with this area? 0, right? And then our area starts going up, but it's getting smaller. And then finally we get to here. What y value do cosine and sine of y intersect at? It's pi over 4, right? So we want to see where these curves intersect each other so we can set those equal to each other. And what input gives both the same value for cosine and sine? That's pi over 4. So that's going to be our upper bound for this. All right, and now we're going to go ahead and do this integral. Now remember, for even powers of cosine, we're going to break out, or even powers of sine and cosine, we're going to break out the half angle identities. So cosine squared is 1/2 plus cosine of 2y over 2. And then y ends up giving us the same thing, or a similar thing. Okay, so notice that this was a minus here. So the minus multiplied by the 1/2 to make that a minus. And then there's a negative attached to the cosine in here by default. So that negative went there. Oops. There we go. And then the nice thing that happens is that this and this cancel out. So we end up with the integral from 0 to pi over 4 of cosine of 2y. Which part of the graph is what? This part is cosine of y, and then this part is sine of y right there. All right, now we just have to integrate cosine of 2y, which isn't too bad. We divide by the number that's in here, and then we do the integral of cosine, which is sine. All right. And then finally, all we need to do now is plug in pi over 4 and 0. So if I plug pi over 4 in here, 2 times pi over 4 will be pi over 2. And sine of pi over 2 is 1. And then if I plug 0 into here, then if I plug 0 in, sine of 0 will be 0. So we end up with pi over 2 for this volume right here. What was the dark blob here? I accidentally wrote an extra 1/2 here, so I scribbled it out. I wrote too many 1/2s. All right, so there we go. So now the question remains though, why did I select to do the washer method here? And how do I know which method to pick depending on my situation? And for this, I'm going to draw the following chart. This chart will help us pick out which method when. Okay, so in the column here, we're going to have function of, and then down this way, we're going to have the axis. So we're going to have function of as the columns, axes as the rows. Okay, so let's say we have y as a function of x, and we're spinning around the x-axis. We already know the answer to this one. This is something that we did earlier in class. We have y as a function of x, so we have kind of just normal f of x, and we're going around the x-axis. Which method are we going to use? Are we going to use the washer method or the shell method? Let's see here. A lot of people are saying washer, and that's correct. So washer, remember, that's the one with a single pi in front and where we square the functions. That was the first thing we did in class. Now let's say we have a function of x and we're going around the y-axis instead. What are we going to be doing then? We're going to be doing the shell method. That's right. Okay, now let's say the situation is reversed and we have x as a function of y. So that's kind of similar to the problem that we just did. If we have x as a function of y, we saw that if we spun it around the y-axis, the washer method will work well. And if we spin it around the x-axis, you could probably imagine that the shell method might be better right here. So these are all 4 of the possible situations here, and this is definitely how I would choose to do them. Now, one possibility, which I'm not really going to go over, is that you can convert your functions from, say, y is a function of x to x is a function of y, and then you could use whichever method you want. I do not recommend that in general, and here's why. So let's go back to what we did in practice problem 2. So we were looking at this area, right? And we were spinning around here. So we originally had this as y as a function of x. But let's say we want to get this as x as a function of y. So what we need to do is we need to get what this curve is and then what this curve is. Now that's not too hard. That's x is 1 and x is 2. But the thing is that this top curve, look at what it does right here. It's 2 for a little bit, but then it changes into this once we get to this y value right here. So what you would need to do is you would need to split up your integral into 2 pieces. One where it's the 2 on top, and then one where it's whatever this curve is on top. And that's annoying. that almost always takes more work than just keeping the same variable that you have and just doing it that way. So if you're ever given y as a function of x, keep it that way and just use whichever method is more appropriate here. That's definitely my recommendation here. All right, let's see here. Oh, that's perfect. All right, so it looks like we're out of time for here. Next class, we're going to begin studying some applications of integration, particularly in physics. So we're going to be doing some physics stuff next time using integrals. So I guess I will see you guys then.